So remember from yesterday, we looked at one variable stats on our calculator. So you're going to be entering data into list 1. Today for our lesson, to speed things up, this is probably one of the few times I'm going to have you actually enter the data. And then you're going to kind of watch up on the board for a lot of it today. But this one we're doing. So remember, in one variable stats, they give you a lot of info, starting with the average. And then it starts talking to you about some summations that you don't really care about because we're not calculating by hand. And then there's the 2 standard deviations that they give you on the 5-number summary. And then after that, on the one variable stat, and then after that comes the 5-number summary. So I don't know how big of a deal I made of this yesterday because I have a short memory, but you cannot use the average, the mean, and the standard deviation to describe your data if your data is very skewed. So if your data is very skewed, you're forced to use a different measure of central tendency and spread. So we're going to be using box and whisker plots. Oh, hot mess. What are you doing? So the 5-number summary, meaning minimum, Q1, median, Q3, and maximum. So remember how we had the descriptive statistics graphic at the beginning of whatever this worksheet's called? Or did we get to that? Oh yeah, we got to that. It was worksheet 10. So we talked about it being skewed right and skewed left, and how I get it backwards because I'm me. So box and whisker plots can also be skewed right and skewed left. So remember how let me back up a few slides. Okay, a few more. Oh, there we go. So if a distribution is skewed to the left, that means like there's screwed up data weird on the tail on the left side. So when you look at a box and whisker plot, what that looks like, what it translates to, is that the left whisker is very long. Remember that kid on that problem yesterday that scored a 30 when everybody else was scoring great? Like he was our outlier and he was skewing the data. So they can be symmetrical, they can be positive or negatively skewed. You might want to add on your notes here, negatively skewed. I will also accept left skewed. Pen. And obviously, negatively skewed is left skewed, positively skewed is right skewed. I just said that backwards. See, I told you. Can't get it right. All right. 5-number summary is what we're going to talk about in this next question. So, it's got to be a good one. It's about shoes. So this employee is doing stats because they're stacking up some shoes. All right, the number of boxes in each stack are given. You should have entered this data into a list. I also entered mine into a list, but I need to figure out where I put that. Are these the shoes? All right, so mine are in list 2. Make a mental note of where yours are at because we're going to go look at some stuff in a minute. Let's start with a picture of it. So let's go to, well, just look at the data for a minute. Do you feel like there's any outliers? Just gut instinct. If you're not sure, it's okay. Questionable. Maybe we need to do the math. That's the right answer. You need to do the math. So go to your stat plot options and then choose whichever plot you want. I'm going to go plot 1. Turn it on. And then down at the bottom of, or the middle here, where it says types, we're going to be wanting a box and whisker plot. And for now, let's just look at a normal one. So the second one that looks like a box and whisker plot is a traditional box and whisker plot. Did I say my data was in list 2? Okay, thanks. And then let's just do zoom stat, because that's always a good place to start, and sometimes it's not great, but mine looks like that. So I don't know. Feeling it's pretty symmetrical? I just hit zoom stat. What'd you hit? And yours doesn't look like this? Something's up. Do you have multiple? Come here. You did select a type. Wait, yes you did. Zoom in, out. Alright, we're going to manually adjust his window. What's the largest shoe stack? Like 15? What is it? 13? Okay. You're wise? That's really weird. They're going 50 to 50, so there's no range. I don't know why it did that. I don't know either. That's weird. Alright, how about not that? You're broken. I don't know. I'm going to come back to you in a minute. Just look at Hannah's calculator for a second. All right, guys, can you go back to your stat plot for a moment? Can you change it to the modified one, the one that comes before the original one? You had your data in list 1, right? Are you sure? All right, and you have it as list 1 right here in your menu? You have it as list 2, don't you? You have list 1? Okay, then I don't know. I'm going to come back to you. All right, change it to what's called a modified box and whisker plot, and then you can readjust the window if you'd like. Do you notice how I don't have any weird little stars and point-looking things? That means that your calculator did the math, and it understands that nobody is out of that outlier range, where it's 1.5 times the interquartile range. So apparently there are no outliers, and you guys were right that a traditional box and whisker plot is fine. Some might argue that it seems a little positively skewed, but I think that's a little too much. I think we're good. So let's come up with the 5-number summary, just because they asked me for it, I believe. And they also want to know means versus standard deviation versus the 5-number summary. So in your menu for stat. Oh no. Guys, we're going to have to throw away this whole video. It's your fault. Anybody else? No? Hey, go to one variable. This video is done. So done with it. There we go. All right. So you just got to threaten it a little. Stat. Calculate one variable stat. Now, remember, my data is where? Mine's in list 2, so make sure you're in the right spot. I'm curious what your calculator's going to do. You do this too. So please jot down, because I think there is a question where they want me to speculate about whether I should use the mean and standard deviation or the 5-number summary. Yep. So jot down all this info, guys. Your mean is 8.4. Do you remember which standard deviation I would like you guys to use for this? I would like you to use the weird Greek letter, the population one. So, James, we're having a discussion about there's times when we have to use a sample. We're going to be comparative data, so we should always be using population deviation because they're their own population. I know, you know a lot about stats, so just forget it for a moment. Just for PreCalc, for what we're going to be doing, use the population deviation. So write that one down. There's your mean. And then please also write down the 5-number summary, starting with the minimum. Okay, I'm going to transfer to my paper. They wanted me to construct this box and whisker plot by hand, which isn't really that difficult. If you guys can tell me some information, because I don't have my calculator anymore. What was the minimum? And then your Q1 and your median, 8.5. And then your Q3 and your max was 13. Okay. So if I was drawing this by hand, which you know is going to be amazing as always, not. This first endpoint whisker is your minimum 5, and then you're going to create, you should probably have an axis if you're doing this on a test, but I'm going to live dangerously. My next component, the end of this whisker, is at Q1, which is 7. And then the median is 8.5. The Q3, the end of the box, is 10. Totally nailed this. Look at that. And then your last whisker ends at the maximum of 13. Yeah, that's not well done, but that's okay. They're relatively in the right order. So that's how you would construct it by hand. Now, we already figured out that there weren't any outliers, but if you were doing this by hand, you would have to then do that 1.5 times the interquartile range to determine if there were any outliers beyond the median. We already know there aren't. So your guys' question is going to be, number 1, do I have to do this on the SAT? The answer is no. They do not make you create this on the SAT. They will have you interpret the data on the SAT, and they will also have you, this is what gets kids, it's not like number answers, it's explanations and the fine nuances between the words that they use. So you have to be careful about how you're interpreting the data. You guys also wrote down the mean and the standard deviation. So they want me to summarize the spread of the data using either the mean and standard deviation or using the 5-number summary. So let me show you a good answer for summarizing the data based on the mean and standard deviation, which I forgot what they were. What was the mean? 8.4? Okay. And then the standard deviation was 2 point something? 2.4? Okay. All right. So, you guys do not know a lot about standard deviation yet, except for you. You do. If you're going to summarize with mean and standard deviation, you have to wait for the second half of our lesson today, because I'll show you what it means to be a deviation out from each side. Okay? Let's talk about the 5-number summary, though. If you're summarizing on the 5-number summary, you're going to say something about the minimum and maximum, indicating the range of the data values, and then you're going to tell me where the middle 50% of the data lies. The box is the middle 50% of the data, which is a more interesting measure of central tendency when you have skewed data. So for 5-number summary, you're going to say the smallest or minimum. What are we even doing here? Number of boxes. Okay, the smallest number of boxes is 5. So the small stack is 5. The largest stack is 13. This is a gigantic run-on, not a sentence, but that's okay. And the middle 50% are between what two values? What was Q1 and Q3? Yeah, those. Okay, I forgot again. What was it? 7 and 10. Thank you. So when I ask you to summarize based on the 5-number summary, basically you're going to tell me the endpoints of the extremes. If there happens to be an outlier, you should mention it then. And then the middle 50% is the really important part for a 5-number summary. Median is cool, but the middle 50% tells your reader a lot more about your data, because that's where a big clump of data is going to lie. All right, so hang tight for the conversation about mean and standard deviation. We talked about the interquartile range. If you do 1.5 times of it, that's how you find out if there's any outliers. This should be written somewhere. Yes, ma'am?
I'm sorry, did I turn my
Yep, you did. So flip to the next page, page 11. And this time I want you guys just to watch, okay? Because this is already entered on my calculator. So I put this into list 3 and list 4. So when I ask you in a minute, oops, list 4, you're going to tell me that, please. So I'm going to go back to my plotting menu, and I'm comparing 2 sets of data this time. So these are the ages of Oscar-winning actresses from 2 different time periods. So long time ago versus fairly recently, if you call 1989 recent. Yeah, you guys weren't born. Okay, that's all right. So they want us to compare those 2. I'm going to open up plot 1. That is where I put the data from a long time ago. So 1969 to 1988. I put that into list 3. And this time I would like to plot, oh, it's already highlighted, but a modified box of Whisker Plot, because I think there's some outliers. I can just kind of tell by looking at the data. Can you guys tell that there might be some outliers looking at the data? Okay. Yeah, there's some strange numbers going on there. It's okay, your calculator will tell you. So that is in list 3. So rather than doing the 1.5 times the interquartile range and calculating off the median, I haven't done any calculation yet, so I'm kind of cheating, but it's okay. And then we're also going to plot the more recent data. Make sure it's on Abruzzo, and it's in list 4. Modified box and Whisker Plot, and it's going to be coloring it in red. Now, when I hit zoom stat, hold on a minute. Sometimes I have extra plots turned on, so I always check that. Now I'm going to hit zoom stat. Do you see what outliers look like now? They put cute little marks there. So what happens is when the calculator does the calculation of median plus and minus 1.5 times the interquartile range, it creates a new minimum or a new maximum, depending on which side of the median you're on, and that's basically the cutoff for the box and for the whisker. So anything that falls outside of that is going to be notated on your calculator by like a weird little box thing. On your paper, usually we notate them with like a star or an asterisk. So it shows that there is a data point there, but it's just not something that I'm going to be considering in my overall data because it's going to skew it. So notice if I change, well, I'm not going to do it because of time, but if I change those to non-modified, they're going to pull those whiskers really positively skewed, and you're going to have some weird data. So either way, let's compare these two data sets, guys, and you don't have to write much down. Let's just kind of talk. So I forgot, I think the blue one was the older data, and the red one is the newer data, although it's not really that new, I guess. Can you talk to me about, let's start with the median, the middle age of the actresses that were nominated? No, winning, Oscar-winning actresses. So who has a higher median age? The long time ago data? Okay. So now we get all societal on us. Why is that? You have any thoughts about that? Because this is where stats is actually used. You know, math people don't run around doing stats for fun. They do stats because there's like an overlying question in society or in psychology or in sociology. AP stats people, or AP psych people, you should be doing a little bit of stats analysis. Anyone in that right now? Do you guys do a little bit of math stuff? Yeah, I mean, it's a big part of stats. So, anyone have a commentary on that? Are they surprised by that data? Are you not surprised by that data? You have no feelings whatsoever towards that data? All right. Good. And I noticed that both the data sets have kind of comparable outliers. So maybe the data is not surprising. Maybe just people are just as sexist back then as they are now. I don't know. I think they're trying to get at the sexism in the acting industry and how there are a lot of pressure on women to act and look younger and younger and younger. Sorry, got all political on you. What, Jenna? You don't have passion about this one? You're very confused today? It's because you don't care about the median age of a Oscar-nominated actress today. No, I gotcha. It's all right. So there's a whole paragraph down there, guys, where they really break down what they wanted you to interpret from this. Now, that's a little much, I think, for asking a 16, 17-year-old kid to look at this data and feel this much about it. But this is what the math says, okay? So the median for the earlier time period is slightly higher than the median from the second time period. But the middle 50% data, I lost my picture, is greater for the actresses from the current, we'll call it current time period, okay? So what does that mean for their overall question about, you know, society and sexism in the industry? I don't know. That's for someone else to figure out. I just do the math, guys. I just do the math. This is good times. Wouldn't it be fun to do a project with your AP Psych class, and then like the PreCalc kids could help everybody out with the math part? I bet Mrs. Lindmark would love that. It's on the internet now, so it's going to happen. But next year. All right, let's take a look at this next question. Yep, real quick. I've entered the data, and I entered it into list 5. So the first thing they want me to do is with this data construct a histogram. Not by hand. Histograms by hand are a pain in the tushy. So we're going on the calculator. And I got all sorts of weirdness happening with my plots right now, guys. I need to turn off plots 1 and 2. Remind me about that in a minute. And plot 3 I need to turn on. Oh, I already have it set up. Yes. All right. So the easiest way to turn plots on and off are just to go up to here and de-emphasize or emphasize them. Turning them on and off. And then I'm going to zoom stat again so it readjusts the window, and it's probably going to, oh, it's not a bad window. Sometimes when you zoom stat, the window's a little crazy, and you got to go back and manually adjust it. Did you ever get anything to graph? Did we just give up on you today?
I got the one bar.
The one very, those came up right? Okay, some setting, I got to figure it out. Okay, so talk about this data, guys. What are your thoughts on the uniformity of it? Do you feel like it's symmetrical? Do you feel like it's skewed to the right or to the left? Or are you feeling this one is very difficult to tell? And basically what you have to do is squint and decide if a big bulk of your data is kind of grouped into the middle sections and then it tapers off onto the sides in a symmetrical way-ish. Yeah, you have very high standards for symmetry. You have me as a teacher. You should be like, yeah, good enough. They're calling this symmetrical. I mean, it's not. The professional stats man says there's no skewedness. He takes stats. He should know. It doesn't look that bad. He's seen worse is what he's saying. Okay, so yeah, this is a hard concept for you guys because when you look at like a uniform, or not a uniform, excuse me, a symmetrical distribution, you're looking for like the perfect symmetry of it. Yeah, life doesn't happen that way typically. I mean, it's cool if it does. No. If we adjusted our window, it actually would look a little more symmetrical than what I'm currently looking at, but they're going to call this one symmetrical. So, fun times. It does say summarize either using the mean and standard deviation or the 5-number summary. So, for now, let's just practice the 5-number summary. So I'm going to go to Stat, Calc. I think I put it in list 5. There's no frequency list, so let's just calculate. Scroll down a bit. So don't worry about constructing the histogram. Just write yourself a little note that that's on the calculator. And then for question B, I'm going to need you to jot down this information. And what is this data about? I have a really bad habit of just like diving into the calculator without even reading the question. That's a terrible habit for a statistician. All right, the average wind speed recorded at a weather station. More fascinating data. All right, so I'm going to write myself a little note. So I'm supposed to be working on a 3B right now to summarize the data. So the wind speeds, speed, range from, let's see, 6.2 to 12.5. Okay. I don't think this is going to be my day, guys. 6.2 to 12.5, is it miles per hour? Is it knots? What are we doing here? Miles per hour. With a median of 9.2. The middle 50%. Okay, my pen's going to stop working. The middle 50% lie between what two values? Thank you. Are between... Why did I choose to write this on my calculator is a better question. 8.45 and 10.45. Now, I didn't really look at the data very closely. Are you curious if there's any outliers? I'm not curious at all, in fact. Okay, so if you're curious or if you're flat out asked, are there any outliers? There's 2 ways you can justify it to me on your test on April, whatever it shows up on. So either you're going to calculate median plus and minus 1.5 times the interquartile range, or you're just going to go and graph a modified box in Whisker Plot, and if it shows you like a weird component that's box instead of connecting the whisker, then you know there's an outlier. At that point, though, bad news, you do have to go find the outlier. So however you find it is up to you. You can use your calculator, or you can go back and calculate it, or you can probably just look at the data and go, pretty sure that's the outlier. But if that's on the test, you have to pick a method for how you're going to interpret outliers. There's a question at the end there. The 10 weather stations with an asterisk have relatively close proximity to one of the oceans. Cool. Except for Atlanta, we discovered, I mean, I've never been to Georgia, but someone told us last year, they're like, yeah, Atlanta's not anywhere near the ocean. And we're like, oh, so bad data. But it does say to construct a side-by-side box and Whisker Plot for just that set of data and see if the wind speeds change. Okay, I don't have time to do that today, guys, but do you have any thoughts about what you expect the data to show? Probably. I mean, I feel like every time I've been on a coastal place, it's been a little windier, but I think it depends on which coast and which part of the coast you're on. I don't know. I don't go anywhere. I go here. Chicago's pretty windy. What's up with that? What? You're crazy. All right, great news, guys. We have time to do what I needed to do today. So find your next page. Worksheet 11, by the way, is your assignment. I need you to work on it in time to get ready for your test, which I know feels very far away, but decide when you want to work on it. The next big test for us is probably going to be, well, it's definitely after your SAT test, so April something. Huh? Yes, 11B. So far you've been assigned 9B and 11B.
So wait, when is SAT?
Are you asking me when you're going to skip school?
Yeah.
Yeah. April 9th. Yes. So you get me for a whole week, and then I don't know what we're doing that Monday yet, but that Tuesday you're going on a college visit. You are. You are. All right, so 11.3, we're looking at worksheet 12. All right, here's my goal, guys. I need to get through at least 12A. Think we can do that? I'm going to go to my resident expert on stats. That's you, James. The normal curve. All right, so the normal distribution is really the heart of your stats class. I feel like you spend a good amount of time on the normal distribution, t-distributions eventually. Yeah, all sorts of good stuff. So what we're looking at here is a lot of people refer to this as a bell curve. When you normalize your data, all the measures of central tendency are accepted to be at the same value. So we're kind of making some assumptions about your data, and we saw in the box and whisker plot, sometimes the data was very skewed, and it would not be mathematically appropriate to then apply a normal distribution to data that's not normal. So you got to be careful about when you're using the normal distribution, and then subsequently we're going to use the empirical rule first. The mean, median, and mode are the middle of your bell curve, or your normal distribution. And then it reads outwards towards what we call the tails, and it doesn't actually end. So you can view the x-axis like having asymptotes. It gets really, really tiny though. Really, really close to the asymptote, right? That's how asymptotes work. So the curve is continuous. All of the area underneath this bell curve would add up to a probability of 1 or 100% probability. So it's a probability curve. It's a graph of probability. It's kind of funky. But it's cool. It's really, it's a good time. All right, so here's some pictures that are not on your notes, but they're from your textbook. So we have some probability distributions, histograms that have been graphed. And notice, as they increase the number of data points, so like this one collected 100 pieces of data, this one collected 1,000 pieces of data, 10,000 pieces of data, the smoother and smoother the curve is looking. Like if you squint and you try to put a curve over the top of it, like it's looking real good. And then all of a sudden they say, you know what, you have enough data to justify that your data can be normalized. And then they start looking at it in terms of a normal distribution. Which is, the possibilities are endless now, guys. You can do a lot of math. So the higher the sample size, the better your data and the more appropriate your stats answers are going to be. We saw some examples just now where we, just for the ease of entering data in the list 1, I didn't give you guys a lot of data points. It was like 11 data points. That's why we were seeing this really choppy histogram. And, you know, James was like, yeah, guys, that's about as symmetrical as you're going to get. Because when you only have 11 data points, it's not going to look good. But, man, on that shoe problem, if that kid had like 10,000 stacks of shoes, we'd be in business. We would have had a much better distribution, right? Or at least a better picture for whether it was skewed or not. That's the formula. Yeah, cool. So we're going to skip that. All right. So let's take a look here, guys. We have a little bit of Greek letter knowledge here. Anybody know who that is? It's like a kitten. Mew.
Mu?
It's Mew. Mew. It looks like a U, but it's Mew. It's Mew. It does represent the mean, which on a normal distribution is all centrals and measures of central tendency, yes. And then later in stats, you have to be real careful about whether you're calling the mean x bar or mu, because James will tell you you're referring to a population versus a sample then. For us guys, we're going to be kind of not picky about that in PreCalc, okay? So we're just going to be normalizing all of our distributions. The standard deviation, remember, this is a lowercase sigma. That's what we're going to be using for standard deviation today. And then what happens is we're going to get to this picture. All right, this will be on a reference sheet that you will get to use on a test. What we're looking at right here is called the empirical rule. And if you have what can be considered normal distribution data, so it can be normalized, the mean is in the middle. Boom. As you measure out, for a certain number of deviations. So like for instance, if you go 1 standard deviation in both directions, so if you add a standard deviation and you subtract a standard deviation, you have 2 symmetrical percent pieces, which add up to 68% of your data lies in that big clump. So big chunk of your data, big chunk probability is where we're going eventually with this, guys. 68% of it lies within 1 standard deviation of each direction from the mean. But if you're willing to go out 2 standard deviations, that'll take you to here and to here. All right, look carefully, Bruiser, right here. 2 standard deviations out, you're going to contain 95% of your data for the population. So there's a 95% probability that you fall within that range. That's pretty good. It's pretty high. And if you're willing to go out 3 standard deviations, oh man, they're not even showing it. It's over here. In either direction, you're going to contain 99.7% of your data, or 99.7% probability. Are that, James, do you remember, are those the same empirical rule numbers you use in stats? Some books just call that 99.71 something else for like easy math. It bothers me. Like Algebra 2 does that sometimes because they're trying to simplify it for kids who are just learning it. Okay. So, guys, what you need to pay attention to, and this is where it gets kind of crazy for kids, all these little components you can add together. So, like, for instance, if I ask you a question in the future where I want to know the probability, or in other words, the percent that lies between these 2 black lines I just drew, well, there's a few ways that we could figure that out. It could be a matter of adding up chunks on the empirical rule graph. We're going to learn later that we can do these on the calculator pretty quickly, and that's where you're going to be the whole time, and that's fine. But first, let's talk about what is called a z-score. So this will be on your formula sheet. In order to use this data, sometimes we're going to have you guys calculate what's called a z-score. A z-score standardizes all data so it matches every other data. So like if I'm looking at, James's data where he has 1,000 data points, and then I'm trying to compare it to my data, I collected 10,000 data points. Our data is going to look different when it's raw, but when we standardize it, we can standardize it to the normal curve where our mean is always going to be a 0. So think about how easy your math would be if that middle number is always a 0. Because then when I make you like add and subtract things, well, you guys got that. You can add and subtract from 0 really cool. Now, I'm going to be flat out transparent here. Once we learn how to do this on the calculator, you guys will probably never do this by hand again. Until you go to stats and maybe your teacher makes you do it by hand, or you get to your AP test where there are parts that were calculator free, I assume. Back in the day, when we didn't have calculators that would do these things for us and find the area under the curve, they had to look up things in charts. So there's only so many charts a person wants to look through, so they had to standardize the data where mean was always going to be 0, and that way James could go to the back of the book and look up, okay, I have a z-score of 1.378, and he'd figure out what area that was. That was a pain. Do you guys have to do that still? So sorry. Oh, well, you're going to learn. I'm going to show you the ways. I think you do. I'm going to be like a Jedi master of laziness with you. You're going to love it. You're going to be like, this is so much better. You do have to know how to do it by hand for your AP test. So I'm not discrediting the way you've learned it. It's important. All right, guys. Let's get to some examples. This first one about monthly temperature. There we go. So you guys are going to be drawing. And since you've learned from the best, they're going to be beautiful. Yeah. Draw a bell curve. All right, let me square my shoulders up. Maybe I have better luck. Nope. Yeah. Okay. Yeah, no, whatever. So in the middle, you're going to put your mean. We're not going to standardize our scores here and make z-scores. We're just going to put the data on here. So the mean, read carefully. Where do they say the mean? This little mu guy. The mean is 65. Then it says you have a standard deviation of 5. So don't worry about so much where you're placing them up and down the curve. Just try to make it symmetrical. So if I go 1 standard deviation up, which is about right there. Oops, I didn't make that symmetrical. You're supposed to be adding a deviation of 5 when you go to the right. So what number are we at here? 70, good. And then you're going to be taking away a deviation of 5, so you're at 60. That was really not symmetrical. Okay, so now let's go 2 deviations out. So whoop, over here. And whoop, over here. Also not symmetrical. Okay, so you're adding 5 more, so 75. And you're taking away 5 more, that's 55. And then let's go all the way to 3 deviations out. Totally. Master grapher here. 5 more, so you're at 80 and 50. So they want to know, without using a calculator here, and we're going to use the empirical rule, the probability that your average monthly temperature is between 50 and 70. We read that between 50 and 70. So here's 50 and here's 70. Okay, there are several different ways we can come up with this. Now, since you guys don't have it on a formula sheet, just look back at the top of your notes. They take this empirical rule thing and they kind of chunk it up for you. Can we be careful though? Because I think there's a little chunk they didn't really talk to you about. Remember how there's 3 deviations here and here? And I feel like they've done you a disservice. This teeny tiny tail and this teeny tiny tail make up the rest of the curve. Well, how much percent is still in the curve if you've already sucked up 99.7% of it? 0.3% of it, okay? So 0.3% is 0.003, but there's 2 symmetrical pieces, right? So we'd have to cut that in half. So there's like a teeny tiny, let's see if I can do this right, 0.0015 right here, and 0.0015 right, oh, excuse me, they're doing percents, not decimals. Back up. So 3% cut, 0.3% cut in half is 0.15%. Can we talk about this number though? Remember how in between these red lines is 95%? Where are they getting the 2.35% from? Because math says 2.5 would be each tail, huh? So what you thinking, Jenna? I think you got it. Yes. All the way down is 2.5%, but between the black line and red line is 2.35%. So here's what I do, guys. When I answer this question, these questions, it's almost done on your formula sheet, right? It has almost all of the pieces that you need. The only thing that I would expect you to add to that picture, either mentally or physically when you get it, is to create this last deviation line and remind yourself that there is a 0.15% on the little tiny tails. It's tiny, but it matters in stats, okay? So, on my question, keep looking at that thing that's in front of you with the percentages. Can you tell me how much percent is in this chunk right here? 34%. So this is another 34%. What's in this chunk right here? 13.5. And then from here to the black deviation line, that last deviation line was 2.35. So if I want to know the total probability between here and here, I think you guys just need to add them up. Now, James, in stats, are you taught to take this number and subtract this number? You're probably taught a bunch of ways, so which would you have, how would you have done that? It's okay, no pressure. Can you guys add those for me though? 83.85, there you go. When I show you on the calculator later, you're going to be like, oh my gosh, that's so much better. But I do want you to be able to do them by hand too, especially if you're moving on in stats. Alright, so this question is, let's do this real quick, guys. I got you for another, oh man. You know, every year I say, you should have pre-drawn standard curves. And every year I go, snap, I don't have pre-drawn standard curves. Okay, who is the mean in this question? Is it 120? Okay. This time we have standard deviations of 16. So when I go 1 deviation up and down, that brings me up to 136 and 104. When I go 2 deviations up and down, that would be another 16. So, thank you, 142 and, what? 150, that makes more sense. I'm panicking because I can't subtract today. 104 minus 16 is 88. Thank you. And then one more. I'm adding the wrong thing. 16 is 168. Thank you. And then take away 16 is 72. Okay. That was really painful. All right, guys. Approximately, now question here is how many trees are more than 136 inches tall? So they're asking me first about all the trees that fall in this area. But when I look at the area under this curve, that's probability, okay? We're going to have to take it one step further in a minute. There's a couple ways you can figure out this probability, but for the sake of us, the easiest way to figure it out is just to add up the chunks. So this was, what, 13.5 plus... Now you can go 2.35 plus 0.15. You could also just say this is 2.5. That's the 2.35 and 0.15 split. Okay. Or added together. So what total percentage is that? 16%? Okay. So 16% of 200 trees would be approximately how many trees? Is that 32? 32 trees. So be careful. Sometimes they want you to take the curve and apply it to some raw data. It's an approximation. All of these are approximations. And then real quick, they want percent between 88 and 104. Well, I think that's a really quick answer, guys. Isn't that just something you pull right off the empirical rule? 13.5%? Yeah. So just read carefully, I guess, is the moral of the story. So you're going to have a wonderful break. You're going to maybe try some questions off of the next assignment. Okay, you're not. Okay. Are you sure? Well, you could. I mean, Hoffbauer's kids will.